whether or not a graph represents a function. Now, I'm going to have you guys on your fun times in your quiz. I could ask you to draw something that shows you have a function or something that shows you don't have a function. So graphically, remember that means vertical line test. If I don't pass a vertical line test, I don't have a graph. That's showing a function. And if I do, it is a function. All right, so we did this one yesterday. We graphed y equal, remember we took this and we solved it for y. Took the cube root of everything. And ended up with that. And then we talked about the parent function. The parent function was the y equal the cube root of x. Now, in that parent function, we had the movements, which again just come from plugging x's and finding y's. We had the movements of left 8, down 2, left 1, down 1, right 1, up 1, right 8, up 2. Why 8, why 1? Because those are perfect cubes. I could put any number in there, but it makes sense graphically. I don't want to graph the decimals, so let's just put 8s and 1s. And all of this is happening from the start point. Now, the start point of a parent function is usually 0. Well, it is 0, 0. But this guy is not starting at 0, 0. It's translating, which means it's moving, and it went 1 to the right. So it started there, and then we did our movements. So from that point, we went left 8 down 2, left 1 down 1. Oh, yeah, because that should be plus. Duh. Well, yeah, I got to add the x to the other side. So you're right, it should be to the left. Left 1. And now we go left 8 down 2, left 1 down 1, right 1 up 1, and then right 8 up 2. And we ended up with that. And then we said, hey, that's a function that will pass the vertical line test, therefore any cube root function is okay. Why is left? Why does it move to the left? Bless you. It is moving to the left because of this. No, actually it moves it to the left. Think about how do I make what's underneath there become 0 again? If I had a negative 1 in there, it would say, right? And negative 1x makes the cube root of 0 equal to 0. So that's where I'm at. So you think opposites for when you're inside your function with the x's, that's where I know right or left. If I was outside of the function with another constant, plus or 4, negative 4, that means I'm moving up or down. The left-right movements, I got to think opposite of the sign. All right, so that passes vertical line test is good. This one over here is not the parent function that we've seen. Y squared equals, if I were to, wow, that's a potent word. So we have y squared is equal to 9 plus x squared if I wanted to solve this. And then I have y is equal to plus or minus. So I'm taking square root here. Plus or minus the square root of 9 plus x squared. So here we can put a table together because again I don't have a parent function with this. We're going to learn about these. These are conics. These are part of our conic section. I think it's chapter 12 is what we're doing. Chapter 12 is conics. We'll get into this. This is a hyperbola-ish looking graph. All right, so what do we do? How do we graph it to see what's happening? Let's put in some values. Okay, first of all, you can look at the radicand, which is the part under the radical. And you can say that thing can never be a 0. I can't take square root of a negative number. Just make that 3 plus x. I cannot. I can't just make it 3 plus x because 9 is not a factor. 9 is closest to the x squared. So anyway, I can't have a negative underneath here. So 9 plus x squared can never be negative. I can say, all right, well, what if 9 plus x squared has to be positive, but it has to be that. And I solve for x squared. X squared would be greater than or equal to a negative 9. And I solve for zeros. There are no real zeros there. So let's just put in some x's and see what we get. If I put in a negative 3, why am I thinking a negative 3? Let's put in a 0 in for x. Let's just start there. What happens if I put a 0 in for x? What do I get for y? I get a square root of 9, which is a positive 3, or a negative 3. Okay, so even without me having to graph it, just by doing this table, I can tell that this thing is not a function. How do I know? I have 2 y values for 1 x value. Yeah, you can't have that. That's not a one-to-one relationship. So with 1 x value, I get 2 y values. So what does it look like so far? 0, positive 3, and 0, negative 3. All right, let's put some other numbers in there and see what happens. Let's put a, we're going to end up with some decimals here. Let's do a negative, let's do a negative 2. Pardon me? We can do a positive or negative 2. Is that what you're saying? Or are you talking to Sophia? Yeah, we can do both positive or a negative 2. If I put a negative 2 in there, or if I put a positive 2 in there, it's not going to change the problem. Because negative squared makes that a 4. 9 plus 4 is the square root of 13. So plus or minus the square root of 13 there. And if I put a positive 2 in there, I get plus or minus the square root of 13. Square root of 13 is what is square root of 13? Square root of 13 would be just shy of, it's between 3 and 4. 3 point something. So let's see what happens. At negative 2, I'd be plus or minus 3 point something. Right about there, and right about there. At positive 2, I'm doing the same thing. Right about there, or right about there. And if I kept putting in values of x, picking my x's, notice that the graph never hits the x-axis. And we already knew that because of this. That means I have no real zeros. But what this graph does do is it just kind of does this thing. Kind of look like that. And this is a graph that has asymptotes. And we could do a vertical line through that, and we would see, hey, it doesn't work. But we already knew that from just our first point. I didn't actually have to graph it. I knew that once I put 1 value of x in, I got 2 values of y, no function. So some of these that are not our normal parent functions, you're just going to plug a t-table, put stuff in there, and see what happens. Yes, Simon?
How did you know what to plug in?
I just picked arbitrary x values.
Is that a plus or minus 13 for the negative 2 and the y?
Uh-huh. So plus or minus for both of them, because if I put a negative 2 in for x, 9 plus negative 2 squared, negative 2 squared is 4. So 9 plus 4, I get plus or minus the square root of 13, and then I get the same thing if it was a positive. So whatever value I put in for x, if I always put in its opposite, I'm going to get the same answer. So that one's not a function. This one was yes. And this one's no. All right, let's do some function work. So we can add functions together, we can subtract them, we can multiply them, we can divide them, we can do what's called composition of functions. That's where you plug one function into another. And we're going to do all of those today. so we've got this rational function, f of x equals 15 over x minus 3. We've got a quadratic function, or g of x equals 16 plus 3x minus x squared. And then we have a radical function of h of x equals 25 minus x squared. Now, we probably know what the green one looks like. We know what the green one looks like? I hope we know what the green one looks like. What is it? It's a parabola. It's an upside-down parabola. Very good. Negative ax squared plus bx plus c. The green one is a negative. It's an upside-down parabola. All right. Maybe not so much about what the blue function looks like and the red one looks like, but that's okay. We're not graphing these yet. We're just trying to find their values at these given x's. So remember, in function notation, whatever this is the x value that I would use. I'm going to replace x with 6. So I'd have in this function 15 over 6 minus 3, or 15 over 3 equals 5. So we'd say that f of 6 is equal to 5. Now, this gives me a point, actually. This is a coordinate of 6, 5. So I could use function notation to find coordinates. It's the same thing as finding a t-table. Pick an x, find your y's. They are the same thing. So function notation gives you a coordinate. All right. What value of x could you not use for this blue one? What would be a no? 3. Why? It's undefined. If you plug a 3 into this bottom x minus 3 part, you get undefined. So in this equation, x cannot equal a 3 because it makes the function undefined. So this is a rational function, and these guys have asymptotes. This one has a vertical asymptote at x equals 3, and it has a horizontal asymptote actually at y equals 0. So these are the kind of graphs that have those branches. So real quick sketching wise, this would look something like, there's my vertical asymptote at 3. And it's going to look something like this. Because I'm going to have an asymptote horizontally at y equals 0, and I have this asymptote vertically at x equals 3. Again, just getting a quick idea of the sketch. If I were to do domain and range on that, we can say, hey, that's a function because it passes the vertical line test. So that's okay. All right, g of negative 7. G of negative 7. Plugging in a negative 7 in there. Somebody do that quick. What are we going to get? G of negative 7. Plugging in. Negative what? Negative 54? Did we get agreement on that? Oh, you got to be careful right there. That's where you got to be careful. Look at that. The negative 7 is the x. The negative in front of that x is not being included in the power of 2. So you have a negative 7 squared, but then there's a negative out front, which makes it a negative 49. So I should have a 16 minus 21 minus 49. And that makes negative 5 minus 49 is negative 54. That's what you guys said, right? Somebody say that? Good job. Way to go. So be careful with negative signs with power. If the negative sign is wrapped with a parenthesis, it gets included with the power. If there is no parenthesis around that negative sign, it's not being effective. Yes. All right. H. H is another unique one because it's got this square root. We know the square roots can have negative values in there. So let's take a peek at that one. We'll look at it graphically too. H of x, 25 minus x squared. Does anyone know what that thing looks like? Nobody knows? All right, let's find this first. What is it? Kind of like that last one, huh? This one's only going to be 1 because you have just a positive root. It doesn't have plus or minus a square root. All right, let's say we plug a 10 into the h. I got 25 now minus 10 squared, or the square root of 25 minus 100, square root of negative 75. We get an imaginary guy here. We get, first of all, an I can come out, and then I have a negative 25 times a 3 underneath there. Or no more negative, just positive 25 now times 3. The I took care of the negative. And then square root of 25 is a 5. So I get that. That's what h of 10 would be. No, it is not plus or minus because, great question, because when we give the original function as a radical like that, that's called the principal root. And that means positive only. We only get plus or minus when I take a square root. So back on that one problem, back on this one. When I had to solve for y and take a square root to get y squared to become just y, that's when you have plus or minus. It's what only when we're plugging in.
I don't understand.
Between when it's plus or minus and when it's not plus or minus? Okay. Okay, here's the deal. In this problem, we go back to this problem. It started as just a radical, right? It starts that way. And when it starts that way, it's always positive. But when you have to take a radical, that's when you make it plus or minus. All right, good question. All right, so what does this thing look like? Again, I can look at the function 25 minus x squared. And I know that 25 minus x squared has to be greater than or equal to 0. Otherwise, I get an imaginary thing in there. So if I solve this one for x, I get 25 is equal to x squared, which means x is equal to plus or minus 5. Now, we just talked about this in chapter 2. If I have this, anytime you have an inequality, you have a sign chart situation. So here I have an inequality that has zeros of negative 5 and 5. I'm looking for positives. So if I plug a negative 6 into this thing, negative 6 squared is 36, and 25 minus 36 makes a negative number. 0 is positive. 6 makes another negative number. So this thing has a graph that is only between negative 5 and 5. This is a half circle. It would look like this. Again, you wouldn't know that unless, one, we've talked about conics, or you graphed it. If you plug those values of negative 5 to 5 into your equation, you would get this half circle looking thing. Is that a function? Does it pass vertical line test? Yeah, that passes the vertical line test. That one would be it. Okay, why don't you real quickly come up with g of 4, f of 0 first. F of 0 plus g of 4 minus h to the negative 3. Let's see if we can get them all on here. There we go. So find that one on the bottom form. Yeah. See how it goes here. All right, so we're checking it out for the next one. This guy. So remember that the f of x function is what we end up removing after we get this f of x plus h out of the way. So first of all, find the f of x plus h. F of x plus h would be replace all the x's with an x plus h. So x plus h squared plus 6 times x plus h minus 3. And then FOIL x squared 2xh plus h squared. Distribute 6h, 6x minus 3. Nothing will be able to combine them because they're all different. So now we have the f of x plus h part we're going to remove from that our x squared plus 6x minus 3 part, and then we're going to divide this whole thing by 3, or by 8. So we're going to subtract out of it x squared minus 6 plus 6x minus 3. Divide by 8. So here's where all of the terms in the f(x) function will cancel with the terms, or 3 of the terms in the f of x plus h. The leading term will always cancel, the negative. The x term will always cancel, and the constant term will always cancel. So we'll go bye-bye, and then I'm left with a 2xh plus an h squared plus a 6h, all divided by h. Then we factor out the GCF of h from the top. Hit those to cancel each other, and I'm left with finding my answer of 2x plus h plus 6 is what that is equal to. Success? Success. All right, last one, then we're going to have a little review FYI slide at the end of this. So again, domains and ranges. Let's try it. Do all of these fit one of my 2 rules that I have to be careful with? They do. There's one of them that has both of them stuck together. All right? So I want you to go solo on this one, or you can work with your partner. That's fine. But let's figure out what is it that I have to be careful with for my x's for these. Talking about domain, what are the x values that help me draw these functions? There we go. So x minus 3, it's underneath the radical. Everything underneath the radical automatically sets equal or greater than 0. When there is just one x, now it's not x squared, it's just x. When it's just one x like this, some of you were doing the sign chart thing, and that's okay. You could do it. You could look at this and say, that has a 0 at x equals 3, and then you might have done your sign chart, and then you test. If I test to the left of 3, 0, I get a negative number. If I test to the right of 3, 4, I get a positive number. But when it's only 1, 0, you don't need to do the sign chart. Just solve this for x. X would be greater than or equal to 3. That is your domain. That's it. Everything has to be bigger than 3 in that graph to make my graph show up. If I'm less than 3, I'm going to get negatives underneath, which are imaginaries, and I don't have a part of my graph right there. Yeah?
On our quizzes and tests, can we just do x is greater than or equal to 3, or do we have to do the fancy?
Okay. Are you calling this the fancy?
Yeah.
Yeah, I'm okay if you just get this.
Okay.
You could also do this. That works too. Informal versus formal. We're not at a dance, are we? No. No, but this is the formal way of representing it. I'm okay if you guys do it. Okay, now this one has x squared, so I'm going to get 2 values of x. So this is a definite sign chart problem because I'm going to have 2 x values and I need to see where I'm going to be greater than or equal. Does anyone have this one, by the way? Who has this? Oh, you guys haven't had a chance to work this one out? Oh, well, then let's try it. You not try it? Do you want me to do it, or you guys want to do it? Let me do it. Sam, you have it? What do you have?
X, negative 6 and 1.
Say what?
Negative 6 and 1.
What about negative 6 and 1? Am I in between negative 6 and 1? So you're saying that you're going to be between negative 6 and 1? Okay, let's see if that's true. Let's see if that's true. So if I set the radicand greater than or equal to 0, why are we doing that? Because it's under a square root. And I factor this guy. x minus, oh no. Oh. We're going to be able to factor this? X plus 6, x minus 1. There you go. All right. Then I use that to find my zeros. And my zeros are going to be negative 6 and 1. And then I test. Test negative 7. Remember, plug it into the factored form. It's faster. Negative 7 plus 6, negative 1. Negative 7 minus 1, negative 8. And a negative and a negative make a positive. 0, positive 6, negative 1 is a negative number. 2, 8, 1, positive number. So we are looking for positives. So that means in my sign chart, it tells me I'm looking for everything less than or equal to negative 6 and greater than or equal to 1. So my sign chart tells me that my domain has to be this. If I'm going to use interval notation. So Sam, you were looking at the negative values, but remember, greater than means positive, not negative. Yes?
So every time you have two sets like that, two sets of rights, then you have to click.
Yes, you do.
Is it always going to be union?
Okay? Questions there on that one? Now this next one, the little beast, a little tricky. Only because I've got some x's in the denominator. So I got to be careful with those. All right, let's go back to chapter 2. And we had a problem like this in our chapter 2 fun science. One of them said, make this a real number, make this an imaginary. This is asking me to solve a square root, which once again means that x minus 3 over x plus 6 must be greater than or equal to 0. Every time I'm starting it the same way. There is no mystery to that. However, now I have to be careful with my sign chart. In my sign chart, I'm going to have zeros, but because I'm dividing by an x, I also have a vertical asymptote value. Remember this?
Is it X?
Huh? Do you remember the vertical asymptote? Why are we having a discussion of asymptotes? Because I'm dividing by an x. So, in this case, what's my 0? We look at the top for zeros. We look at the denominator for vertical asymptotes. So we have 3 and negative 6. Those create the values on my sign chart. If you remember, what we did with these is I suggested that you circle the vertical asymptote because you can never be equal to that. Now in this problem, we can be equal to a 3 because that makes the 0 in the top. But I can never be equal to the 6. So we test. Negative 7. Negative 7 minus 3 is negative 10 on the top. Negative 7 plus 6 is negative 1, and a negative over negative is a positive. 0 would make a negative 3 over a positive 6, which is a negative number. 4 would make a positive 1 over a positive 10, which is a positive number. And I'm looking for the positives. So I'd say anything from negative infinity to negative 6, but do not include. And again, I'm not including because that's a vertical asymptote value. Union it. The 3 to infinity. And that would be the domain. Okay. So you're going to have to practice this stuff, folks. You're going to have to wrap your head around this. Reading our book, hopefully. Right? It's not just, if you just in here, put your time in when I'm doing stuff on the board, it's not going to be good. You got to do your time outside of class. You got to read the book. You might have to even get online, look at some other stuff. Go back and review what we did. All right, here's just a summary now. This is not, you can just hold off on writing anything down on here. And I would suggest that you go and peek at this. There's also on YouTube, on the Darren Pagel YouTube thing, there is a review of these parent functions. How do we get them? So so you might go check it out. Just a down, dirty way of coming up with graphs very quickly. Table-wise, I'm thinking again of movements. So we're going to have 6 that we look at right now. The other 2 are our exponential function and log function. We're not going to look at those. We're going to see those in honors time. So here they are. Our linear function, also known as identity. Domain on that thing, we already said it is equal to what? It's all reals. Now, how about range? We haven't talked about range yet. Range is the y value. Take that graph and squish it onto the y-axis. What are the range values of a line?
All real.
All reals. Yeah, because they've got arrows going both directions. Okay, let's do the same thing now with these other ones. So remember that an absolute value graph is a V. So this one had domain of all reals. It had a range of all reals. What about the domain and the range of the absolute value? Domain's all reals. Look at the graph. It just keeps going forever in both directions. So, yeah, it has a domain of all reals. How about the range, though? Y is greater than or equal. Don't just say greater than or equal to 0. You have to specifically state y is greater than or equal to 0, or you would do your interval notation for that thing. So I can be 0, and then everything above. Again, if I take the graph and I squish it onto the y-axis, I see that everything from 0 up, I would get something. All right, parabola. Same thing. Yeah, parabolas and these absolute value functions, parent function-wise, they are the same thing. Again, we can flip these things over. We can move them. It doesn't matter where I move them. What makes the difference is if I flip them, then my range is now upside down. Instead of being greater than or equal to some value, I would be less than or equal to some. Square root, we've already done this one. Squish it. Where do I land on my x-axis when I squish the graph down? Positive values? How do I say that? X is greater than or equal to 0. All right, squish it onto the y-axis. What do we get? Y is greater than or equal to 0. Why did I write reals? Why in the world did I? All right. Okay, cubics and cube roots. We already talked about those types. They're like my linears. Everything works all the time. Squish it onto the x-axis, it all squishes. Everything value of x works. Squish it onto the y-axis, everything works. Do the same thing with the cube root. Squish it onto the x-axis, everything works. Squish it onto the y-axis, everything works. Even though it looks like I kind of have these flattened out parts, they don't flatten out. They keep going. So everything works. Domain and range for these are always all reals. All right, so those are our parent functions. Again, if you knew them, it helped you thinking about conceptually the shape of the graph. And then lastly, again, FYI, translations, that's when we move the graph. And translations occur up or down when you have some constant value outside of the function, f(x) plus or minus k. Plus moves up, minus I move down. We talked about inside the function with the x's. You have left and right movements. So it's x plus, we're going left. And if it's x minus, we're going right. So you might want to peek at this, and again, look at the, maybe check out the review of parent functions on the YouTube. All right, questions? George?
From the top,
Yes? The parabola one?
the parabola and
Yeah.
the V.
Yeah?
Why is the V all reals?
Okay, good. Why isn't the V all reals for the range? All right, look at the graph. Here I go. I'm going to squish this thing. Take this thing and push it over here. All this stuff lands right there on the y-axis, right? Same thing on this side. This stuff all goes over here and lands. There's nothing happening below that V vertex. There's nothing on the graph on the y-axis below that. So you see it? Nothing down there. So it can't be all reals. All reals would mean I have something going on down there in the negative y, and I don't.
So is the parabola negatives too?
The parabola is the same thing. Notice if I take this, wrap it onto the y-axis, everything above 0 works, but there's nothing below 0 on the y-axis.
Wouldn't it be better than zero?
Yeah. Oh, yeah. Yeah, poor guy. Yeah, thank you. Wondering what the heck? There we go. Did I do the same thing on absolute value? No. Okay. Well, yeah, you're right. It should be greater than or equal to 0. All right. Did I mess anything else up? Is it all okay? I think we're okay there. Sam, do you have a question? No. Simon?
I did, what kind of topic have you covered on the quiz?
All right. Sections 1 through 3. Composite functions like we've just been doing. Lines, writing equations of lines.